Hi everybody! We're going to start chapter 4 today, and chapter 4 is all about everything quadratic. Quadratic functions, quadratic equations, quadratic expressions. We're on notes number 15. I suspect that you have had a little bit of experience with quadratic functions and probably a decent amount of experience with factoring quadratic expressions, but you're probably not an expert at this topic. So there's a lot of new information to cover in this chapter this year. And we're going to start with graphing quadratic functions. We're going to start with the most basic quadratic function, y equals x squared, or as you see here, I've called it f of x equals x squared. Perhaps you already know what this looks like. I'm going to show you my tips for how to make it easier to graph these by hand. So first of all, typically, if you don't know what something looks like, you're going to plot some points. So I'm going to make a little table of values, just some kind of typical choices like -3, -2, -1, 0, 1, 2, and 3. Let's see if I can get a little more space here. Remember, f of x is equal to x squared, so we're going to square the input. -3 squared is 9, -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. Okay, I think I'm going to make my scale go by ones on both axes. 9's up here. Okay, so we can plot these points. -3, 9, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, 3, 9. And then, of course, there would be infinitely many other points, and they're going to form this shape, which, sorry, mine is kind of wiggly. Make it nice and smooth, not pointy. This is a parabola. This is our parent function, y equals x squared, our most basic parabola, and then the rest of them come from this. We'll be using transformations and other ways to figure out how to get to other parabolas. Notice the symmetry. We have symmetry across the y-axis. So if you were to fold it on the y-axis, it would line up with itself. That line is also known as the axis of symmetry. Okay, now suppose that we wanted to graph f of x equals 2x squared. Let's think about what we've learned about transformations. Multiplying a function by 2 is going to stretch it vertically. Stretch it vertically by a factor of 2. So 2 times as tall. So I'm going to go ahead with the same scale, and I'm going to double the y-coordinates of the points that I plotted previously. So 0, 0, double the y-coordinate, it's still 0, 0. 1, 1, double the y-coordinate, now it's 1, 2. And reflect that over to the other side, we also have -1, 2. 2, 4, double that, double its y-coordinate, and you get 2, 8. Reflect that over to the other side as well. And I'm not going to be able to fit the point 3, 9 doubled, so we'll just leave it at this. Okay, so twice as tall. Now, here's my little shortcut the way I like to think of it. When we graphed the first one, we started at the vertex. We went over 1, up 1. In both directions, over 1, up 1. Well, now we go over 1 and up twice that. So this is over 1, up 2. In both directions, over 1, up 2. And with the first one that we graphed, when we went over 2, we went up 4. Over 2, up 4. In both directions, over 2, up 4. So when we multiply it by 2, we go over 2, up 8. So you double it. In both directions. So when you're graphing a parabola, it's not like a line where you only need 2 points and then you can connect them and get the shape, but I would say at least 5 points is best. And so if you just start at your vertex, over 1, up 1, over 1, up 1, over 2, up 4, over 2, up 4, or whatever the stretch is, you'll have your 5 points. So let's apply that to problem number 3. So notice we're multiplying by 1/2. So the graph is going to be half as tall. We're going to multiply our y-coordinates by 1/2. So we'll still have the point 0, 0. Instead of over 1, up 1, we go over 1, up what? That's right, up 1/2 in both directions. And instead of over 2, up 4, we go over 2, up what? Half of 4, so just 2, so over 2, up 2 in both directions. And as long as we have the space, instead of over 2, up 9, we would go over 2, up 4.5 in both directions. So for me, it's just nice to have that little phrase, over 1, up 1, over 2, up 4, and then adjust it because it's a quick way to get those points. Remember to make it smooth at the bottom, not pointy. Okay, let's talk about the main features of quadratic functions. And we're going to start with a form that we call standard form. There are different ways to write the equation of a quadratic function. Standard form looks like this. Y equals ax squared plus bx plus c. So what makes something quadratic? When we say that something is quadratic, what we mean is its highest exponent is 2. The exponents have to be whole numbers, 2, 1, 0. You can't have an exponent of 1/2 or something for it to be a quadratic function. Just whole numbers, and the highest exponent is 2. You could be missing the term that has an exponent of 1. You could be missing the constant, the term that has an exponent of 0. But you can't be missing the term that has an exponent of 2 or it won't be quadratic. The shape, so the noun is parabola. The shape is a parabola. And the verb, or maybe it's the adjective, I guess. Yeah, the adjective is parabolic. We have a parabolic curve. The y-intercept. So we know for any graph, the y-intercept is the point that has an x-coordinate of 0. So if you take the function, put 0 in for x, all you're going to have left is c, that constant value there. So the y-intercept is the point 0, c. I always like to have my y-intercept as an ordered pair, so 0, c. Okay, we're going to come back to the vertex in just a minute and the axis of symmetry. We're going to look at a few examples to get the information from that. Now, some parabolas open up, some parabolas open down. The ones we graphed earlier all opened up. But remember what we learned about transformations and what we learned about reflections across the x-axis. If we were to take the equation and multiply it by a negative, it would flip upside down across the x-axis. So if you see a negative number as your leading coefficient, as your value of a, if that is negative, then it's going to open down. If that is positive, it opens up. So opens up if a is greater than 0, opens down if a is less than 0. If it opens up, the vertex, which is this point right here, is going to be at the bottom. So the y-coordinate of the vertex is the minimum value. Sometimes we just say minimum. The minimum value of the function. That's the lowest y-coordinate you could get. If your parabola opens down, then the vertex is at the top, so no point will have a higher y-coordinate, so the y-coordinate of the vertex will be the maximum value. If you're asked where is the maximum, you could give the x-coordinate, but if you're asked what is the maximum, you would give the y-coordinate. Remember, we're going to come back to that vertex and axis of symmetry. So I graphed 3 different parabolas using my calculator, and I pasted their images in here, as you can see. And I also graphed the axis of symmetry. That would be the fold line. So if you were to fold the function on that line, it would match up. So we see with the first equation, it opens up. You have a positive 7 as the leading coefficient. We see the axis of symmetry has equation x equals 5/14. And actually, the calculator gave me the coordinates of the minimum. And that minimum x-coordinate, 0.357, blah, 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 that's actually 5/14. Now if we look at the second one, notice it opens down. The leading coefficient is negative. The axis of symmetry has equation x equals 1/6, and guess what? The maximum is at the point with x coordinate 1/6. That makes sense, that the vertex would be on the axis of symmetry. So whatever the axis of symmetry is, that tells you the x coordinate of your vertex. And then if we look at the third one, it has a positive leading coefficient, so it opens up. And it's just on the y-axis. The vertex is, the axis of symmetry is x equals 0. You'll notice the calculator might not give you exactly 0, but if you think about what this is saying, 1.8083 e negative 7 means 1.8083 times 10 to the negative 7th. So that's 0.00000018. That's basically 0. Okay, your calculator is approximating it, but you can take that to mean 0. What I want us to do is look at the equations and look at the axis of symmetry equation and see if we can see the pattern going on here. This is not a proof, but we're looking for a pattern. So what do we notice? Well, let's look at the numerator of the axis of symmetry. And for the third one, 0 is the numerator. It's 0 over something. We'll just fill in that box in a moment. How does that number correspond to your equation? Well, in the first equation, there's a negative 5, whereas the numerator of the axis of symmetry is 5. In the second equation, there's a 1x, and we have a 1 there. And in the third equation, there's a 0x. It's invisible, but notice that there's no x term, so we'll say 0x, and there's a 0 there. So it's looking like the numerator of the axis of symmetry has something to do with that middle number, the coefficient of the x term. We could call that the b value. Remember, we have y equals ax squared plus bx plus c. Now, how about the denominator? So we have a 14, we have a 6, and we don't know really about the third one. 14, how does that relate to the equation? Well, that's 2 times the 7. 6, that's 2 times the 3. We just have to ignore the negative, I guess. And then I suppose if we wanted to, we could make the denominator 8 on the last one, and that would be 2 times 4. So what are we arriving at? Looking at the first one, we could say that the axis of symmetry has as its numerator the opposite of the b value, and as its denominator 2 times the a value. Will that pattern hold for the next one? If I do the opposite of b, I would get the opposite of 1, negative 1. And if I do divide by 2a, I would get 2 times negative 3. So negative 1 over negative 6 is positive 1/6. Yep, that works. And then for the third one, we know the opposite of 0, our b value, would just be 0 over 2 times a. 2 times 4 would be 8, so that works. Okay, so we get 2 things out of this. We get, I'll quote Miss Cornell, we feed 2 birds with 1 scone. I know the phrase is usually kill 2 birds with 1 stone, but this is a better phrase. We feed 2 birds with 1 scone. 2 things for the price of 1 here. We know the axis of symmetry is going to be the opposite of b over 2a. Let's fill that in. It's going to be x equals the opposite of b over 2a. It's a vertical line, so we have to write the x equals part. Don't leave that off. And because the vertex goes through the axis of symmetry, or I should say the axis of symmetry goes through the vertex, we know the vertex will be the opposite of b over 2a, comma, whatever the y-coordinate is. Okay, so let's do some examples. It's probably a good idea for me to make the examples as part 2, and we'll just have 2 videos today.